So in this part of this lecture, we will see about the Boolean functions and the algebra, Boolean algebra. So you see, in the last class, in the last part of the lecture third, we saw that that there are various gates and how to implement those gates. Okay, what is the functions of those gates and what are the symbols of those gates. So we have seen different things related to the gates in the last class. Now in this class we will see that when we combine some gates, okay, so then what happens. So combining some gates, what happens, we can implement any Boolean expressions, any given Boolean expression. So that Boolean expression is useful to implement. I mean, you can implement the hardware with the help of that Boolean expression. Now the hardware which we want can have like many type of circuits. So it can have less number of gates, more number of gates. So the question is that which circuit will be suitable for fabrication. If you want to like make an hardware on an IC integrated circuit, then which circuit will be more useful. So it is very, obvious that the simple the circuit is, and if the circuit have less number of gates, the better the circuit will be called. So our overall aim is to make the circuit with minimum number of gates, so that the circuit should be simple to implement, it should be cheap, and the cost is also less, and it will be fast also, because you see every gate we are using is made up of a transistor, and in the transistors there are many phenomena which takes place, because of which the output is not available instantaneously when you apply the input. So there is some time delay. So that time delay will be more if you use more number of gates. So to reduce all these things, we want the circuits, the digital circuits, to be very simple, and that's the simplest circuit can be found if we are able to get the simplest Boolean expression. So you see in this particular slide, let us see that what are the different type of circuits which we can have, and then how to reduce it. Okay, so that will be the discussion of next three parts of this particular lecture. So in this you can see that of particular function, let's say the function is something a dot b dot c plus a b c bar plus a bar c. So you can implement this particular function in various ways. Okay, what are these identities and all the things which we are, this particular identities we are going to see in this part of this lecture, that how to get the reduced form of any given expression, if it is possible to. Okay, so let's say you have been given this function, okay, first the red colored function, and you can directly implement this function with the help of gates. So this color function you can see with this particular, you can match these colors. So this red color equation, Boolean expression, can be implemented with this first diagram. So it is nothing but this first gate. So there is a 3 input gate, you can observe, you can see it that it is a 3 input gate, so ABC. So this term you can implement with this gate. Then this term, to implement this term again you need a 3 input gate. So this is also 3 input gate, and you can see that the various inputs are A, so A is coming from here, then the other input is B, so B is coming from here. So this input is also not an inverted input, it is a direct input from B, whereas the third input is there as well. So this third input is a complemented input, so we are getting here. Okay, so this term, this particular gate gives you this term A B C bar, whereas the third term is A bar C, so that is implemented with this gate. Okay, now if you OR them together, then you get the expression this. So this is one of the way to implement this expression, but with the help of Boolean identities, which we are going to see in this particular class, we may reduce this function. Okay, so one of the very popular identity which we are going to use in our future discussions as well for the K-map as well as the tabulation method. So this particular identity is a very useful identity in simplifying any given expression. Okay, so this particular identity will be used, is the basic formula which is used in the K-map as well as in the tabulation method, because of which you can do all the simplifications. Okay, so you see what we have done is, in this particular from these two terms we can take AB common, and the remaining things are C and C bar. So this can be left here, and this remaining term, So now you can see it is very well known, if that suppose C is 0, so then C bar will be 1, or vice versa. If C is 1, then C bar will be 0. And from your very basic things, you know that 1 plus 0 will be always 1. Okay, so C plus C bar will always give you 1. So that is what it means. That is why I have said it is very simple. So this, and then this particular thing can be reduced to AB, because C plus C bar is equal to 1. So this particular expression can be reduced in this form. So this expression you can implement with the help of, not this one, so this one above equation. So this equation, green one, can be implemented with the help of a certain different circuit diagram, certain different hardware structure. So this hardware will have different type of gates. So you can see here in this circuit, you can find that there are 3 input, 3 AND gates, 2 NOT gates, whereas an OR gate. In this circuit, you are using 3 AND gates, 2 inverter, whereas 2 OR gates. Okay, and the number of inputs are also different. So the same expression, the green one, you have implemented with this green circuit. Okay, rather by reducing it further, as we have discussed it already, you can reduce the function like this, AB plus AC bar. Okay, by applying the identities. So then you can implement again the same function with the help of a third diagram. So that third diagram is given as the Brown equation is implemented with this particular diagram. Okay, so you see this again is the same implementation, same function you will get, same functionality you will get, but the same function is implemented with less number of gates. So you see the same function, the point is the same function can be implemented with different number of gates. Okay, or the different hardware can be required to implement the same function. So which hardware we should use? So I have already told you that we should use the simplest hardware. So in this particular question, this hardware will be more suitable because it have less number of gates. Okay, so this is what the reason is. But we should have some method to reduce this function, a given function, whichever function is given to us, then we should know some techniques to reduce that function in the minimum form. Okay, so in this particular the next few parts we are going to learn these techniques. Okay, so if we discuss at the very broad level, okay, so then there are 3 methods basically to reduce any Boolean expression, to simplify any Boolean expression, any given Boolean expression. So the 3 methods are the Boolean algebra method, which you might have seen in your last semester. So from your previous courses you may be knowing this thing, that what are the Boolean equations and what are the Boolean identities, and by using those Boolean identities how you can reduce the function. So probably you may be knowing it, but if you are not knowing it, then we are going to discuss it here. Okay, so I'll introduce all those identities, though I am not going to prove those identities, but I'll just show you the identities and you can simply prove them as well. If you want the proof, then you can go through the book and can refer your previous semester's course as well, because in this particular course we are not going to use this Boolean algebra very much in detail. Okay, this Boolean identities we are not going to use to reduce the function, and the reason for that is this Boolean identities are useful to simplify the expressions, the Boolean expressions which have less number of variables, okay, less number of literals. If the functionality given is a little bit complex, then it becomes difficult to implement or to reduce the function with the help of Boolean algebra, okay, because it becomes a little tedious to do all these things. So we just avoid that, okay, but still we will learn it, because this is the basis for all our future techniques. And if you remember this Boolean identities, so it will be useful to implement other circuits as well. So that is a sort of good introductory thing, a good foundation. For a good foundation also you require it, and it will be useful for your future topics as well, some of the times. Okay, not always, but at sometime it may be useful. So we'll try to understand those identities as well, okay, without proof in fact. Now there is another technique to simplify any Boolean expression. The other technique is Karnoff map. Okay, so that is K-map, that is very popularly known by the scientist who has invented it. So by the name of the scientist who has invented it, and the technique is called as K-map. So this technique also we are going to learn. Okay, so one by one we will learn. And the good thing is you can apply any of the technique to reduce the function depending upon your proficiency, because any method except the tabulation method, in fact as far as manually we have to do, so the tabulation method also. So any of the method will the implementation of this method will depend upon the your proficiency. So how much proficient you are with these methods. If you're not proficient, then it will be difficult for you to do the things, okay, rather any of the method. So the point is you can use any method to implement the to reduce the function. So we'll learn each one of them sequentially, okay. So Karnoff map. The Karnoff map is what we are going to see is we are going to see the Karnoff map for 3 variables, 4 variables and 5 variables, okay, up to 5 variables. But with Karnoff map, K-map also, the difficulty is that it is like dependent upon the human being who is applying that method. So it is human dependent what answer you are going to get, okay. Because if you are not proficient, you may make mistake in forming the groups and like applying the techniques. So that is also the thing. But you can become proficient by practicing, by continuously, by regular practice, okay. So if you have sufficient practice, then it is not a problem. You can use any of the method until and unless it is not specified in a particular problem. So if it is like specified that you have to use a particular technique, then it's better to use that technique only. But this method also, K-map, is suitable for up to 5 variables, okay, 6 variables you can use it. But beyond 6 variables, it becomes very tedious, very difficult to solve the K-maps. Okay, in fact, I have not seen any in any book that the K-map has been solved with 7 variables. Okay, so I have seen up to 6 variables. So this K-map also can be useful for up to 6 variables. But when you, suppose you are implementing something as a processor. Okay, you want to implement a processor for a computer, let's say. So it will have little more number of variables, because nowadays if you see the computers, they are 64 bits, right? So 64-bit processor. So there is, we are talking about 4 and 5 variables. So 4 5 variables is like nowhere, stands nowhere. So 4 5 variables is the function with 4 or 5 variables which it can have at most. But in 64-bit you can have 64 variables. So it is very difficult to simplify the functions in such a complex system, for such a complex system. So if you want to use this the simplification for those cases where the number of variables involved are too many, then we go for the other method, which is called again known by the scientist who has invented it. So it is known by the scientist's name. It is Quinn-McCluskey method. Okay, and the other name for the method is the tabulation method. So this method is suitable for your automation. If you want to suppose automate the simplifying technique, then you can use this method. So in the computers, to simplify the expressions, we use this tabulation method. Okay. So this method is suitable for any number of variables. Okay, you can go up to any number of variables, and then you can program this method. So this is what the good thing about this method. But for small number of variables also, if you try to implement it, then you can implement it, but it will become tedious. So this Quinn-McCluskey is more suitable for for the questions or for the problems which have 5 or 4 or more number of variables. Okay, so we'll learn each of this method. Okay, what is the procedure? First we'll see the procedure in detail, and then we will understand the things with the help of examples. So let's start with Boolean algebra. So Boolean algebra these are the simple identities of Boolean algebra. So when you say that it is you want to solve something with the help of Boolean algebra, so you have to remember some rules. Okay, they are the rules similar to what you know from your basic mathematics, from your arithmetic. So suppose you have to implement let's say some addition you have to do, or some multiplication you have to do. So you remember certain rules, right? So similarly, if you have to, when you want to perform some manipulation on Boolean expressions, then also we have to apply some rules. So in this part particularly, we are going to see those rules, and these rules are based on your operators. Okay, so some operators will be involved. So these operators are, as you know very well, that they are AND, OR and NOT. Okay, and the Boolean variables can have only 2 possible values, so 0 and 1. So these are the various simple Boolean algebra rules. So you know that this particular thing. So we will discuss both of them. The name is also there. The name is not that much important. Okay, if you want to remember the name, then it is very good. By just naming this particular identity, you can recall it, or if it is written, you can easily understand that which identity it is being talk of. But I won't talk about this names. I will talk about these rules as well. Okay, and not the proof, but directly I'll tell you that these are the how it is possible. So you see 1 dot x. So x can have any value like 0 or 1. So if it is like 0, the answer will be 0. If it is 1, then the answer will be 1. 1 dot 1 will be 1 and 1 dot 0 will be 0. So in fact, at any place, if you just substitute x by 0 or 1, then you can see that whether what you can get. So if you are getting suppose x itself, okay, the answer is changing with respect to x, then you call it x. Or if it is not changing, if it remains the same as in the second identity, you can see that 0 into x. So if you multiply 0 with anything, the answer will remain 0 only. So here I have shown 0. Okay. Then x dot x. So if you multiply 0 with 0 or 1 with 1, then the answer will be 1. So there is nothing. These are very simple identities. So no proof is required for them. But if you want, you can go through the book, or like these are the identities. So no proof is required for them. You can directly remember them by the logic as well. But if you want them in detail, then you can refer the book as well. Okay. Then the other identity is x dot x bar. So obviously 1, if you take x as 1, complement will be 0. So the answer will be 0. If you take x as 0, then complement its complement will be 1. So answer again will be 0. Okay. Same is here. Excuse me. So same is here. You can see, you can implement it OR form. So 0 plus 1, 0 plus x, sorry. So it will be x, 1 plus x, 1. X plus x, obviously 1 plus 1 or 0 plus 0 will always give you same. So that is what it is written here. X plus x bar will always give you 1. Okay, 0 or 1, you take 0 or 1, 1 or 0. So it will be 1. No change. Okay. So these are the simple rules. So in few slides we are going to see these rules. Okay, next few slides. So other rules. So as you know from your algebra that x into y or a dot b is equal to b dot a. So the same rule follows here as well. So x dot y is equal to y dot x, or x plus y plus is equal to y plus x. Both are true and both are equal. Distributive law, associative law. So associative law says that x dot y, if suppose there are 3 variables involved, so if you do x dot y and then to this particular product, if you multiply z, so then that will be equal to x multiplied with the product of y dot z. Okay, so that means this. Then in the OR form you can say that if you sum 2 variables and to that sum if you add a third variable, then that will be equal to this other thing. So x plus the sum of the other 2 variables y plus z. Okay, third identity. So this is like difficult in this form to understand, but you can easily understand if suppose you use them in x instead of x, if you make x dot x. Okay, and if you simplify it further, then you can say, you can easily understand that it is x plus y and x plus z. Okay, it is not difficult, but it is very easy to understand it from here. So x dot y plus z. So x dot y plus z will be equal to how much? Xy plus, because you are multiplying it inside. So xy plus xz. Okay, so see, for this particular, if you are finding it difficult to understand, you refer the book. It is not difficult, it is very easy. You can directly, you will be able to directly understand it from the book. Okay, so I won't waste much time in this identity, but it is simple. By just putting x plus x bar or something like that, you can prove it easily. Okay, so let's see the other identities. So I have tried to include the important identities only. Okay, it is not sort of the exhaustive list. I have not included all the identities probably. So if you want more identities, so refer the book. So the other law is x dot x plus y. So what will happen? Again you apply these identities, or you can see this x plus x y. So absorption. Okay. So whenever the situation is something like that, x plus xy. Okay. So then that will be equal to x. Why it is so? So you see, it is very easy to understand. It's not difficult. So if you take x common from this, then what will happen? X will come outside. Then you have 1 plus y. So 1 plus y. What will be 1 plus y? 1 plus y is obviously always 1, because y can have only 2 possibilities, 0 or 1. and if you add 1 to any variable, so then it will always give you 1, right? So that is why these identities always will come to x. Okay, so it is easy to understand. Similarly with this, again you can use x dot x plus xy. Same logic can use and can implement it. Okay, so it will come same. Then De Morgan's. So this is the one of the most important identity, and this can be proved with the help of the truth table. Okay, it is very easy to prove this identity with the help of truth table. So what you do, you take the one half, right half, okay, right hand this equation and the left hand equation. So left hand and right hand, you take both of them and then just make the truth table for the left hand part and the right hand part. Okay, and try to see that what output you are getting. So if you are getting the same output in the truth table, then you prove that the identity is true. So this identity is one of the most important one. Okay, so De Morgan's law. So because this identity and the other identity, probably one more identity I have already told you, x plus x bar. So these two identities we are going to use during the course as well, many of the times. Okay, but you should know the other identities as well, because the other identities may also be required. Okay, so this identity De Morgan's says that x dot y whole bar. Okay, I'll just give you the mathematical expression. You can know the statement for this from the book. So x dot y whole bar, what you have to do is just divide the bar. Okay, or if the bar is divided, then add it up. So here the bar is added up, so x dot y whole bar. So then what you do, you complement it completely. So it will become x bar plus y bar. So if there is an ANDed function, then you get an OR function, so that they will be equal. Rather, if it is something like that, x plus y whole bar, then what you do, again the bar is combined, so you can separate them, and you complement this operator as well. Okay, so x plus y whole bar will become x bar dot y bar. This is very important to remember. Okay, and this vice versa is also true. If you get somewhere x bar dot y bar, by the help of De Morgan's, you can easily make it x plus y whole bar. Okay, or otherwise, if it is x bar plus y bar, then you can easily make it x dot y whole bar. So this identity is very useful. It can easily convert an NAND gate to an NOR gate, to this OR gate, or inverted OR gate, or an NOR gate to an inverted AND gate. Okay, so you see, this is what the beauty is. So that is why you can that is why this identity is very much useful, because it is helpful to implement the any given function with the help of NAND or NOR gates. Now you know this very well, that double complement. So x double bar, so complement of the complement will give you the same variable. Okay, so then De Morgan's law. So De Morgan's law, I have already told that it is very important, one of the important identities. So it can be used for any number of variables. Okay, not only for the two variables, but it can be used for multiple variables. So let's try to understand this De Morgan's law with the help of a certain example. So let's suppose the function given is f is equal to xy plus x bar z plus x z bar. Now you want the complement of this function. So suppose you want to find the complement of this function. So what you will do? What will be the complement? So you complement this all. Okay, so if you complement this whole thing, then what will happen? You can use the De Morgan's. Okay, so to apply De Morgan's, you should have the complete bar over this expression, first thing. Or the second thing is that to combine, the otherwise, if you want to have it, if you want to apply this De Morgan's, then there should be bar over each of the term. Okay, like say this one, this, or this. So you can use any of this. So usually we simplify the De Morgan's for the equations which have like complete bar. So in this case, if you apply De Morgan's, remembering from your previous slide, what we will do, we will separate the bar, we will divide the bar, break the bar. So break the bar. So if you break the bar, then it will come, the broken bar will come over to this expression separately. Okay, each one of them. And then when we break the bar, we invert the operator. So if it is an OR operator, we make it AND operator. So you see, we have inverted. Okay, so break the bar and invert the operator. So that is what we have done. So if we do this, then again you see x dot y whole bar it is coming. So break the bar. So you have broke the bar. Okay, so you have broken this bar, and then after breaking the bar, this invert the operator. So you did that as well. So same for here, same for here. Okay, so x double bar plus z bar. Okay, then y bar plus z double bar. So double bar also we have seen that it will also be this double bar is equal to the variable itself. So you see, this is how you can use the De Morgans to simplify the expression as well. Okay, so this was the simple example with the help of this thing. So this is a summary of all the identities which we have seen in last few slides, and these identities will be useful to you for simplifying any given expressions. Okay, so this is the utility of it, and with the help of this simplification expression, you can implement that expression with the help of your AND, OR and NOT gates. Okay, or with the help of NAND and NOR as per your choice. So now let's try to simplify some problems, some Boolean expressions with the help of the identities only. Okay, so let's say, so whatever identities we have learned so far, let's use those identities to simplify this given expression. So this is a 3 variable expression. So there are 3 variables x, y and z, and the expression given is x plus y plus x plus y bar dot x dot z bar and over whole bar. So if you want to simplify that, then how you can do it? You can use certain laws. I'm not going to name the laws, but I'm going to explain you this. So what we do is, this is the given thing, so we write it directly. Then just what we do is, see, this term we left it like this, and here we have applied De Morgans. Okay, so let's see whatever easiest way we can do. So first of all, if there is a complete bar, implement this De Morgan, so apply De Morgan. Now once you have done this, then see, there are a few things which we do. So if some variable is missing in a certain term, so we try to multiply or by that variable, or like add that variable. Okay, so something like that we do. So we can rewrite this equation by multiplying. So we have multiplied this part with this part. Then see what will happen. If you multiply this x plus y with x plus y bar, then you will get this expression, and then this part is same as this. Now if you further simplify it, then what will happen? X dot x will give you this. Okay, then this particular is y dot y bar. Okay, so y dot y bar will always be equal to 0. So later on this term will become 0. Then from this term and this term, so you have written them separately, then this and this. So again from this term you can see very easily that x is coming common. So in the next step we have taken x common, so y plus y bar. Okay, and this is remaining same. Now in the next step you can see that, as I have told you, y plus y bar is becoming 0. So this 0 x, then x y plus y bar. So y plus y bar is equal to 1, right? And x bar plus that. So further reducing, this equation becomes something like x and x plus x. Okay, so it is x plus x is again will be x. So x, 1x is written here. Then x bar plus z. Okay, further if you apply your distributive law, then it will become this particular. If you further apply the same laws which we have used already, so it will become xz. So you see, this expression particularly was looking so big, but you have reduced it to xz. So this is the beauty of these identities. But I am not that good in remembering the identities. I don't remember all these identities, and it becomes difficult for me particularly to solve the problems with the help of identities. But if it is required, then you can use your logic to solve these things. But I have given you a certain example, one example with the help of which you can understand the logic. More examples, many more examples, you can find it from the book as well. Okay, so the thing is, you can implement this particular function with the help of gates, or you can use this function to implement the same function. But the good thing with this function is that it will require only one gate with 2 inputs. But this function will require more number of gates. So from our logic, we know that we should be able to implement, to reduce our cost, make it fast, we have to use this expression. We should use this expression, okay, to make it the cost, to reduce the cost, to make it fast, and to get their advantages as well. Okay. So let's see the other example. So the other example is, can take many number of examples you can use to solve any number of any question, any Boolean expression. Whatever Boolean expression I'm going to solve in this particular lecture, okay, whether it is by K-map method or the Boolean expression method or the tabulation method, you can use any of the method to solve that problem, okay, to solve that Boolean expression. So it is your choice. I'll solve problem depending upon in which region we are. So here we are solving with the help of Boolean identities. Later on I'll explain it with the other methods. Okay, so here in this problem, let's say it is again a 3 variable expression. So the given expression is this, and we have to reduce this or minimize this expression. Okay, so again we will use these identities. So your expression is, you see, this is the given expression a. Okay, somewhere I use bar and somewhere I use this complement, because using complement, this particular symbol. So both these symbols are okay, but whichever symbol you are using, be consistent with that. Okay, so in the previous problem I have used that, but here I have used this because it is easy for me to understand write the equations with the help of this symbol. So f is equal to, you can see the given expression. Now the very first thing which the De Morgan's, so we just look for the De Morgan's. So if there is any possibility to apply De Morgan's, apply De Morgan's. So you see here I can see the possibility of applying De Morgan's. So if I apply the De Morgan's here over to this, then I find that okay, this can be reduced. So break the bar and invert the operator. So I have broken the bar here and inverted the operator as well. Okay, so each of the term is inverted. Then rewrite this equation in the form. So again De Morgan's. So again you can break the bar and invert the operator. So again same thing we have done here. Okay, De Morganized it. Then here, so now multiply them. So after multiplying we get this expression. Then after that simplify it by using this your common sense, a bar dot a bar, it will give a bar only. Okay, so similarly now multiply this c bar with this c bar. After this, whatever function you are getting, so reduce that. Then reducing it, we get reducing and applying the distributive of this distribution of this a multiplying it with the other variables, this opening the this bracket. So opening the bracket we get this. Then the final answer is AB. Okay, so is it the same problem? I don't think it is same problem, but it is looking like more or less same. So what it is? X plus y? No, they are different, but the answer is of similar type. Okay, so I thought it is the answer. The problem is different. Okay, so maybe so you get the same type of answer, right? So this is how you solve it. This is how you use the identities to solve the problem, right? Then there is one more important thing. So that important thing is your duality. Okay, so complement is something different and dual is something different in Boolean algebra. Okay, so if it is in a certain problem you have been asked to find the complement, so then find the complement. But if you want to find the dual of something, so then that dual is also possible. And why we study dual at all? So you see, whenever we talk about the dual, it means that the same function, because you see why we require dual. So dual is first of all required because there are two type of logic which exists in the Boolean, in the digital logic, in the digital electronics. So you have positive logic as well as the negative logic, and we very well know that what is a positive logic and the negative logic. Okay, so you see what happen if suppose I use positive logic and make a certain gate, let's say AND gate if I make. Okay, and if I just invert the logic, then what will happen? The AND gate will start working as an OR gate. Okay, and if you have implemented an OR gate in the positive logic and if you just invert the logic, then it will become the other gate. Okay, so if you have made an OR gate, it will become AND gate. If you have made an AND gate, then inverting the logic, the gate will become OR gate. Okay, so you see it automatically changes. So it means that A dot B, if it is A dot B, so the dual of A dot B should be A plus B. Okay, so you see, not A plus B. If the you see what is happening, A dot B. So if you are making A dot B, so the dual of that will be what? It will be A plus B. So this is what it means. Okay, so whenever we have to implement the dual of something, so by just implementing the logic, So if we want to find the dual of something, what we do is we just replace all the plus signs by the negative by the dot signs. That is, we make all our OR gates, we convert our all OR gates to AND gates. Okay, or if it is an AND gate combinations, then we convert it to OR gate. We replace all ones with zeros. If in an expression there is any 1 or 0, so we reduce the ones, or we interchange with ones by zeros and zeros by ones. Okay, but the important thing is we do not complement the variables. That is why I have said that if the function earlier was a dot b, then it will become a plus b. Okay, not a bar plus b bar. So that is what I was telling you. So if I would have asked you to make the complement of a dot b, then you will put a complete complement. Then it will become a bar plus b bar. Then, because you see, you will apply De Morgan's then. So a bar plus b bar. So complement is something different and dual is something different. So why this dual comes in the picture, first of all, we should understand that. So I have tried to explain that. So you see, this is what the purpose of dual is. And the good thing with the dual is that you don't have to prove that this duals separately. So if you have proved a certain identity, then the dual of that identity will also be true. Or if you have proved it in one form, vice versa, the other form will also be true. So this is what the good thing is. So if one form is already proved, then we assume that the other form is also true, or the dual is also proved. So with the help of certain examples, we will understand that how to find dual of a certain given expression. So I have in the last slide I have told you the method, that how to find the dual of this. Excuse me. So we'll solve this examples. So we'll find the dual of this certain questions. So let's say if the identity given is a dot 0 is equal to 0, and this is true, then its dual will also be true. So if the identity is a dot 0 is equal to 0, then its dual you can write very easily. So the variable will remain same. So if it is a, so it will remain same. Then the other thing, the other rule is that you have to, this, if it is 0, then you have to make it 1. If it is 1, then you have to make it 0. So interchange them, and interchange change the operator as well. So the operator here is AND, so we will make it OR in the dual. So if it is written a dot 0 is equal to 0, the dual of this is a plus 1 is equal to 1. Okay, so you see, so the dual of this will be this. Okay, the last slide, you follow the rules from the last slide and get the dual of anything. So if you want to suppose find the dual of this, a plus c dot a complement plus b. So following the rules, we won't change the literals. Okay, literals will remain same. So if you have to follow this, then what will become? A plus c is equal to a plus c dot a complement plus b if it is equal to a dot b plus a complement dot c. So the dual of this will be what? A dot c, okay, plus complement. We are changing this operators. Then it will be, because there is no 0 and 1 involved, so no need to follow the, no need to, the second rule will not be applied here, but we'll just keep the literals variables the same, we'll interchange the operators. So doing that, you get this particular. Okay, so this I have already read it out. Okay, so this will become a complement dot b, right? The other part is a plus b dot a complement plus c, right? So see, this will find the dual of this. So if it is given like 0 and 1 is also there, so we have to make the dual of this also. So you try this question by your own. If you suppose I have to write the dual of this, so what will be its dual? It will be a plus b. So this is the question for you. Okay, so find the dual of this. So you pause this video and then later on see this, what will be the answer for this. Okay, so what will be its answer? I'll tell you the answer, but you pause the video and try to solve it by your own. For this particular case, I'll tell you. So the dual of this is a plus b complement, then dot a plus b plus c. Okay, and there will be complement of this whole, because we don't have to change the variable itself, because if you suppose we consider this as a variable, then the complement will be there. You try for the other term as well. Okay, and then see the answer. Okay, so I won't show you the answer, rather you try it by yourself, and if in a doubt you then ask me. Okay, I have told you about the one term, the second term you try by your own. Here it will be 1. Okay, that is for sure. Okay, so moving on to the, okay, so I'll stop this particular lecture, this part here itself. In the next part we'll see the other method, okay, the K-map. So thank you for listening this.